Hi, I'm Tarique Siddiqui. I recently graduated from UIUC and I'll be joining Microsoft Research soon. Today, I'm going to present our system ShapeSearch, a visual data exploration system for pattern matching in Trendlines. This work has been done in collaboration with Paul, Zesheng, Professor Karahalios, and my advisor, Aditya Parameswaran. So, shapes over trend lines are routinely used for characterizing real-world processes. For example, in medical science, rising and falling trends of gene expressions are used for measuring the impact of drugs. In astrophysics, shapes with sudden dip or rise in brightness trends of stars are used to discover planets and supernova. Shapes of stock price trends over time are often used for forecasting future market behavior. For example, recently there has been talks on economic recovery paths from V-shaped to U-shaped to shoe-shaped. And finally, doctors often examine the shapes of physiological signals over time for diagnosing potential diseases such as heart attack. Experts in most of these domains lack sufficient programming expertise. Hence, a number of systems that support query-based sketch interfaces have been proposed for making search for patterns easier. This includes our previous system, Zesheng. These tools let the domain experts draw or drag or drop the shape that they're interested in, and the system automatically finds matching visualizations. However, these tools lack a number of important features common in pattern matching tasks over trend lines. First and foremost, most of these tools try to exactly match the drawn trend line. As a result, many visualizations that have the same trends but do not precisely match the drawn shapes are skipped. Second, these tools lack support for partial pattern searching. It is common for users to search for patterns where they do not precisely specify the position, duration, or intensity of patterns. For example, one may be interested in finding stocks whose prices are decreasing for an unspecified period of time. Similarly, it is cumbersome to search for complex shapes that involve multiple patterns often combined using conjunctions, disjunctions, or quantifiers. For example, one may want to find stocks that are either increasing or decreasing, or ones that had two peaks in the last 6 months. And finally, there are some tools that perform pre-processing to index the desired shapes in advance. However, these tools are not a good fit for real-time ad hoc data exploration, as applying different filters on the fly can significantly change the shape of trend lines. So to address these limitations, we developed ShapeSearch, a flexible, expressive, and efficient pattern matching system for trend lines. It has 3 key components. First, it supports multiple specification mechanisms for approximate and partial pattern matching. Internally, it leverages a compact and rich algebra for composing a wide variety of shapes. And finally, it uses an efficient shape matching engine for ad hoc and interactive pattern searching. So this is the ShapeSearch interface. On the left side panel, ShapeSearch allows users to upload their data set and configure the search parameters. After uploading, users can search via 3 specification mechanisms, namely natural language, regex, and sketch. While the sketch interface allows precise shape matching, very similar to other query-based sketch systems, natural language and regex interfaces are often used for flexible and approximate pattern matching. Here's an example of a natural language query for finding trend lines that are first increasing and then decreasing. After submitting, ShapeSearch immediately shows the parse query in a correction panel where users can edit it if needed. You can also specify the start and end positions for a more constraint matching or search for multiple shapes at the same time. With regex, users write a more structured query directly using ShapeSearch primitives and operations. For example, the regex in this slide finds trend lines that first decrease from 2 to 6, then increase from 6 to 10, and finally end with a decreasing pattern. Clearly, such queries are very hard to express or parse using natural language. ShapeSearch also allows users to mix and match regex and sketch to search for more custom shapes. For example, I can first sketch a peak and then use it within a regex query to search for trend lines that peaked at some point in time. All natural language regex and sketched queries are internally translated to a shape algebra. Shape algebra consists of a small set of primitives and operations that help compose a large variety of shapes on the fly. Our core primitives are shown here in the slide. We developed this algebra after many discussions with domain experts from genomics and astrophysics, as well as after studying a large corpus of pattern queries collected via Mechanical Turk. We show in our paper that this algebra is quite expressive. It can capture a rich variety of pattern matching queries involving sequences, conjunctions, disjunctions, quantifiers, as well as various constraints on the width and locations of patterns. For matching, ShapeSearch approximates trend lines with line segments, as line segments are effective at capturing trends and are very efficient to compute. The shape matching gets fairly complicated if we have many different nested and or operators in the query. However, in this talk, I will focus on the simplest case of a single sequence of patterns and show how we address it. For complex shape matching, please see our paper. So as a first step, ShapeSearch approximates trend lines with as many lines as the number of trends or patterns mentioned in the query. After approximation, score of each pattern is computed as the function of slope and other properties of the line. Finally, scores across trends are aggregated depending on what operations are used in the query to output the final score. However, the main challenge for matching is that for a given query, there can be many possible line approximations. The exhaustive exploration can be extremely slow, taking several minutes even for a small dataset. In our paper, we explore the shape matching problem with respect to our algebra and show that pattern matching using shape algebra satisfies the optimal substructure property. For example, in the shown visualizations, the matching of last two patterns in the second subregion is independent of how the first pattern is matched in the first region. Using this idea, we develop a dynamic programming algorithm. Unfortunately, even the DP is too slow as its runtime is quadratic in the length of the trend lines. So for developing a faster and more interactive algorithm, we make two observations that help reduce the search space. First, we note that in the optimal approach, all points of the trend line are considered equally important. However, trend lines often have local minima and maxima, which are more important and are quite representative of the overall shape of the trend line. So they can be used to reduce the search space. Second, the process followed by the optimal approach is pattern agnostic. The space of exploration remains the same regardless of what patterns are specified in the query. However, if we look at the patterns in the query, many poor approximations can be skipped by exploiting the local trends in the trend line. So based on these two observations, we develop an extremely fast approximate algorithm that makes realistic assumptions to reduce the search space. We call this algorithm as segmentary, and it involves a pattern-aware bottom-up matching. We can describe the key steps of the algorithm with a simple example. Say we were looking for a shape which was first decreasing and then increasing over this trend line. As the first step, we split the trend line into multiple smaller contiguous subregions. Next, for each of the subregions, we find the optimal matching for every sub-expression in the query. In this example, we look for the best decreasing and then increasing patterns in each of the subregions independently. By doing so, we are able to identify important points that are more relevant to the patterns in the query. We call these points as locally optimal points. After finding locally optimal points in smaller regions, we repeat the process over bigger regions by merging two regions at a time in an incremental bottom-up fashion. Over bigger regions, we find locally optimal points using those points that were locally optimal over smaller regions. Thus, the search space is much smaller. We continue this process until all regions are merged and we reach the overall trend line. Well, clearly, this algorithm is approximate. In our paper, we showed that it is optimal under certain realistic assumptions, and its runtime complexity is linear in the length of the trend line n and raised to the power 4 in the number of patterns k specified in the query. The length of the trend line is usually very large, while the number of patterns is very small, often less than 5, since it is specified by the user. So k to the power 4 is typically very small. In addition, with aggressive pruning techniques that we discuss in the paper, we can reduce the runtime even further. For evaluation, we conducted performance experiments as well as performed a user study and a case study with genomics researchers. For performance, we looked at 5 different datasets and issued queries varying from then 2 to 6. We compared the runtime latency of our segmentary algorithms with a number of variants of shape matching algorithm, including the TTW and the optimal DP algorithm. We can see that while the DP and DTW take many tens of seconds, the segment tree is substantially faster, taking only a few seconds in the worst case. On comparing the accuracy of bottom-up with results of the optimal algorithm, we see that the segment tree always gave an accuracy of more than 85%. 85% here is not bad, given the actual matches was essentially indistinguishable. So overall, we see that the segment tree algorithm results in comparable accuracy to that of the optimal approach with very interactive response times. We also conducted a user study with 24 participants and compared ShapeSearch with ZenVisage, our own system, and Catch, both are recently proposed query by sketch systems. For a fairer evaluation, we turned off the query by sketch feature of ShapeSearch. We used 7 pattern matching tasks commonly used for trend lines for evaluation. Overall, our results show that ShapeSearch leads to faster exploration as well as higher accuracy over tasks that involve searching for one or more trends, sub-patterns, or ones that involve complex constraints on the X or Y axis or the durations of the trend. On the other hand, sketch-based systems perform better for tasks that involve more precise matching or shapes that are very hard to express in words or via regex. This was expected because Sketch works better for those tasks, and recall that we had disabled the query by sketch searching for ShapeSearch. When asked about their preference, a large majority of users found ShapeSearch useful. Compared to the baselines, many said that with ShapeSearch, they felt more confident and were in more control of what they were searching. This finishes my talk. You can find more details about ShapeSearch on our project webpage and the technical report. Thank you for your attention.